Okay, so welcome back. Now we're going to discuss something called angular velocity. Okay, so let's talk about velocity in general, and then we'll fill in angular velocity. So if we look at velocity of a particle moving in a straight line, right? So velocity is equal to what? Distance over time. So it's going to be the distance s divided by time t. So that's what we call velocity. So we could calculate average velocity of a particle using this formula where v is the average velocity, s is the distance traveled, and t is the elapsed time. Okay? Now, what if the object is moving in a circle though? Well, if it's moving in a circle, it's going to be a little different. Okay, and the angular velocity is calculated a little bit different too. Okay, because of the fact that it's moving in a circle and not on a straight line. Because if we were talking about a straight line, then the velocity of the particle would be this velocity right here at this point. Okay, but that's not what we're doing. We're trying to find the angular velocity, how fast is it moving on a circle. And that's where the circumference has to come in because, again, arc length, right? Right? Arc length. So in this case, our angular velocity is given a little bit differently. Okay, so let's do this. So let's do an angle here. And so there's S, here's R, and here's theta. Now the angular velocity is going to be how fast is it moving from here to here. Okay? So in other words, let me do this. And we use the W, or actually lowercase omega, to represent angular velocity. Okay, so V is known as linear velocity, right, straight line, and omega is used for angular velocity, which is the object moving around a circle of radius r. Okay, so now, when the object is moving in a circular path with a constant speed, the distance traveled is the arc length. So now we've got S as the arc length, right? Through which it moves. So therefore we're going to divide both sides by t. So what we're going to do is we're going to start with arc length, right? So distance, right? So again, think of what this is. The velocity is going to be distance. So this is linear velocity, right? It's distance over time. Well, think about this. Arc length is equal to, so S, the distance, arc length is equal to theta times r, right? So if I divide this by t, I get that, right? So we're going to call this, because now we're using angular distance, right? Arc length. We're going to call this omega, and omega is going to represent angular velocity. So this is linear velocity, right? This is angular velocity. So we would rewrite this as theta over t times r if you want. And so that is the formula. Okay? Now, here, oh, hold on a second. Oh, I'm sorry, this is wrong. This is angular velocity. So this is still linear velocity, but now what we did is now we've got linear velocity and we've have theta over t. So this is theta over t, so we're looking at the change in the angle divided by t times the radius. This is angular velocity. So this then is written as omega times r. Okay. So the result is this. Linear velocity is going to be equal to angular velocity times the radius, where angular velocity is theta divided by t. Okay? And I think that's it. Is there anything else I need to say? Okay, so a couple of things before I let you go. So notice that this line here represents the linear velocity, right? This represents angular velocity. Notice that the direction is linear, but as it travels around the circle, this line is changing, so the direction is constantly changing, okay? But it's still linear velocity. Angular velocity is how fast the angle is turning, okay? How fast it's moving that way. So again, just to reiterate that. Oh, also, even though this is radians per unit time, okay, is angular velocity. So angular velocity is given to you as units, radians per unit time, even though that's the units here. Typically, they talk about revolutions per minute or something similar. So when we talk about angular velocity in real life, in practice, it's usually revolutions per minute or something like that, something similar to that. Okay, so that's it. Now we'll do some examples.